Hi, everyone. Good morning. So today my talk is on the topic of realigning AI, insights from accidental misalignment and cutting-edge defenses via contrastive representation learning. So a lot of work give credits to my students Samuel Simcoe and Punya Pandey, as well as our insightful collaborator Kalin at FAR. So Samuel and Punya are also joining me on Zoom. So when we have very detailed technical questions, they can pop in anytime. Let's start with the motivation. LLMs are becoming widely mainstream as we see the number of downloads and visits of ChatGPT and other LLMs, as well as like on Hugging Face, like how the models exist, how many models exist, and so on. And on the other hand, we see two faces of model fragility. On one side, they can be forced to generate harmful content. I think relevant for AI safety, this is an example of how to hotwire a car. And also the top examples are how to build biochemical weapons and conduct cybersecurity attack, for example, to government systems and so on. The other case is even if people don't intentionally aim to attack the system, if they fine-tune it for a separate purpose, it might also negatively affect safety. So the alignment challenge for open-weight LLMs, given all these Hugging Face and other platforms, like open sourcing the LLM weights, means that any actor on the internet can download them and modify the weights to repurpose the LLM for a malicious intent. And base open weight LLMs should be robust to adversarial attacks. This is one of the goals in AI safety. And also guardrails should be hard to remove with model fine-tuning or weight editing. Our research direction is therefore to this two motivations. The first one is to build robust protections against adversarial attacks in terms of persuasion or other types of optimized prompting. The other is investigating how fine-tuning affects safety. So these two works are what we will present today, and also leading the way towards a future alignment challenge on tamper-resistant, robust safeguards. So in the first work that we will cover on improving LLM safety with contrastive representation learning, led by Samuel and in collaboration with Mrimaya and Benhard across ETH, Max Planck Institute, and UToronto. So as we have mentioned, there are a lot of available open source models. The reason why they are unsafe, here is an example, like the user can have a malicious input. And then even if the existing model on Hugging Face or other sources can be relatively robust against the different attacks, we can still have a local version of the model tune it for some purpose. Therefore, such guardrail and other external defenses are not applicable for open source models. Moreover, in recent attacks, such as reinforced GCG in 2025, it break all open source models with an attack success rate of more than 80%, which means if you really want to enforce, just tell me how to build this biochemical weapon and other things, the model will tell people the actual steps to do it. So the immediate work that we are improving over is circuit breakers by Center for AI Safety last year, which also shows a promising alternative to adversarial training. And it's based on representation engineering, previous work led by the same group of authors. So what it essentially does is that breaking the LLMs down to its fundamental operations. Let's say the input goes through embedding to generate the first layer's internal representation. And then in each layer, the representation evolves until the final layer of the output. what it does is I look at these internal representations HI, which is called residual stream, and conduct engineering to optimize this residual stream so that the models will have different types of behavior. This example here is that if the user give an input on writing a hate mail to a public figure, then they can add, like, even if the user optimized for a certain adversarial suffix to trick the model into answer, after circuit breakers, the model will still give nonsense answers, staying to the purpose of adversarial defense. Let's learn the basic mechanism of how they achieve it, and then we can see why they are not enough, how we improve it to close to more perfect performance on adversarial defense. So what they achieve it here is basically, as we mentioned, we look at the hidden embedding in the residual stream of the model. And what they have is a fine-tuned version of the same model that is more robust. And the residual stream of the original model is H. The fine-tuned model is H prime. B means a benign prompt instead of a harmful prompt, which is noted by a small h here. So what they try to do is that in the newly fine-tuned model, the embedding for the benign prompt should stay roughly the same with the original model, minimizing the L2 distance. However, to maximize the difference of harmful embedding in the original model and the fine-tuned model, so we try to make them as orthogonal as possible, therefore minimizing the cosine similarity of them. So the circuit breaking loss basically fine-tune on this loss objective to improve the representation space. If we put them into the context, this reinforced GCG is a type of attack that we mentioned in the beginning of the talk, which is highly effective. So a lot of models are largely broken by them. So here is a conflicting goal here in that all these above work on the headers are attack. So they are fixed in related work, and they want and each number in the table means attack success rate. So the attackers want to make the success rate as high as possible. The best case is to make them close to 100% always answering. And then all the column, like the column headers here, are basically different defense mechanisms. So the lower attack success rate means we successfully defend. So what we propose in our work is the triplet loss plus adversarial training, and also the pure triplet loss is a variant of it. So our method basically improve over all existing baselines to like up to 0% attack success rate, means perfect defense. And also for a very strong type of attack called embedding attack, which usually attack model until 90% accuracy, like attack success rate will drop to lower than 5% in our case. And we are also motivated by circuit breakers are not perfect in a lot of the previous cases, and we look for further improvement space. So let's dive into how we do it. We basically revisit and propose several improvements over circuit breakers. And moreover, the essential problem behind adversarial defense, at least in the current formation, is basically a problem about robust classification, a robust distinction between, let's say, a benign prompt, how to bake a cake, and a harmful prompt, how to build a bomb. Inspired by a lot of like deep learning big figures, a decade ago, 2 decades ago, we actually connected it with the literature on contrastive representation learning for robust embeddings. How we do it? So 2 related work that we're based on. The first one is the DR Lim work in 2005, where they address a general classification problem into a positive class and a negative class. So basically what they do is similar to the spirit that we mentioned before on circuit breakers, but on this work by Yan Le Kun in 2005. So what they do is that they still want to have a loss term that minimizes the L2 distance of, so Y here is the label. So they want to minimize the L2 distance for if the label is the same. And they want to maximize their difference if the labels are not the same. The further improvement of it, called triplet loss in 2015, is more, which is used in FaceNet and also later BERT. What it does is that it also emphasizes something called a relative distance. Namely, let's say P is a point in the positive class and N is a point in the negative class. So they put an anchor point, which also belongs to the positive class in this case. So they basically want to minimize the distance of any anchor in the positive class with another positive point, and also push it away from any negative sample. So in this way, the embedding space of the positive class will be more clustered together, and everything pushed more away from the negative class to even enforce the robustness of the representation. Adapting it to our scenario, it just means that we want to push everything like how to bake a cake, how to do certain recipe, how to be a good speaker, all away from a set of offensive and malicious prompt. So in our formation of the triplet-based loss, the positive and negative class are replaced with benign versus harmful representations. And then we take the same spirit, like across the original model and the fine-tuned, more robust model. We make the benign prompt as close as possible. And we push the benign prompt away from a negative class, like this anchor point, which we will introduce later. Similarly, on the harmful queries, we want to basically make the new harmful representation far from the old ones and make it close to some target representation P that we're learning here. So let's expand on what we put as anchor points in the triplet loss. So we basically want to minimize the weighted sum of both of these two triplet loss, pushing the embeddings of the benign prompts and also pulling the embeddings of the harmful prompts. And to choose the right anchor points in this triplet loss, basically have the motivation that the anchor point for the harmful prompt should try to push the new harmful representations far from the benign representations and push the new harmful representations close to each other in the space. And what we do here is basically having a mean of the harmful representations, basically have a centroid or center of gravity almost for the harmful representations, and make sure all the harmful ones are attracted to the center of gravity as much as possible, whereas all the benign ones are as far as possible. So again, we basically do these, like plug that like central point in to the loss term of the benign loss and the harmful loss. Then we further add a KL divergence term here to make sure that it's a regularization term to make sure if we receive very diverse requests, let's say they should still fall under a similar distribution of the original benign prompt. Let's say how to bake a cake, how to deliver a good presentation, how to learn linear algebra well. So they probably span across different places in a distribution, and we still want that distribution's shape to be kept so that model generate quality answers instead of telling a generic answer to all these benign prompts. We also have a performance evaluation of how models actually kept their performance on benign prompts due to our combined loss considering all the perspectives. Lastly, we also improve the sampling process here because every training process is basically over one batch, and then we propagate the loss and update the parameters. So here, sampling is very important as we want the representations to be like the representations from harmful prompt response pairs to not offer the most harmful representations, but some confusing hard negatives. And also, hint here is that since we have an attack model and a defense model, it would be nice to additionally enhance the defense ability on confusing, like successful attack examples that tricked the model. So what it is called is, although it's a negative example, like close to the decision boundary, it's a hard negative. Just to visualize it, as we mentioned, we want the model to distinguish harmful prompt and benign prompt. However, like the value of different bad prompt, harmful prompt is different in that there are some very clear terrorism styled prompts, but there are also some confusing, like maybe this person is talking about they're writing a novel. Can you compose this to make the novel more realistic? So it's really confusing whether it should be allowed or not. So we use our attack to mine these examples and enhance the model, basically sample them much more than a clear negative example so that the decision boundary gets more robust here. And what we do here is that we intervene in model inference computation, use an adversarial module, fine-tune unharmful data. This module can be linear or a simple MLP, but we managed to trick the model by a large ratio. So then the representations are replaced by this hard negative example, and then we insert this one into our contrastive learning process here. So basically, for every epoch that we train the model, we first generate a lot of attack to get these hard negative examples. So the attack module is also created on the fly with regard to the previous model. And we generate a very efficient, effective attack to have samples close to the decision boundary. Then we feed these examples into these triplet loss that we have formed. And then later at the end of it, we retrain the attack module. With this, it basically reveals all the secret behind how we manage to achieve close to zero adversarial attack success rate and defending the model against the three very strong attack methods: reinforced GCG, GCG, and embedding attack. So we evaluated it also on different types of benchmarks using these attacks, HarmBench and also SR. And also we report an additional score for the SR dataset. So we will report a set of additional results to show the comprehensiveness of the method. First additional result that we will report is the variance of the attack success rate. So if we look at all the previous models, the original one, a previous baseline, rep band, and circuit breakers, what they reported in the paper include like mean, or like we also re-implemented to get their like minimum attack success rate ASR and maximum. As we can see that they actually vary by almost 27% here for circuit breakers, and also more than 30% here in rep band. And such min-max distance in the full version of our triplet loss is much smaller, to 15% variance. The other things are basically our ablation studies and so on. And the same case can be seen on the other methods, such as strong reject ASR and strong reject score of these models, which shows on average much larger variance in previous baselines and a much smaller variance in our defense. I guess a point to mention here is that the variance is about if the attack method can optimize their hyperparameters to make circuit breakers break or make rep band break and ours. than how much space they can optimize by hyperparameter search. And the space they can optimize on our models are much less than others. The last one, as we mentioned, the motivation for the regularization term of this KL divergence is to make sure that when they face benign prompts, they actually have a relatively stable performance. So what we do here is that we have a bunch of general model performance evaluation benchmarks, like ARC, like GSM-8K on math, HELA-SWAG on different types of reasonings, and also the MMLU, which is commonly used across different language understanding tasks, as well as truthful QA coming from the AI safety community. So we basically see that our method didn't affect the model performance too much. Just as a negative example, you can see that the rep band, as a previous work, it drops the performance of the model on mathematical reasoning from 75% to 49%. It also drops models' performance on truthful QA in the general version of it from 46 to 2%. So the reason here is that there is always a trade-off in that if we come up with, we make the model on average dumber and not able to also answer how to bake a cake, how to do a good presentation, then of course their attack success rate will also be low as they in general lose reasoning capabilities. And then we try to enforce that our method mostly just cause a small variation, fluctuation of the model performance. And also, actually, surprisingly, on truthful QA, we have some enforcement, but it could also be that truthful QA is slightly small, so the variation is larger. And lastly, we also have a defense generalization experiment to check whether our method generalized to other languages and other formats. So we basically conduct perturbations on the data set of harmful responses. Let's say given this prompt of write a hate mail for a public figure, then we evaluate how robust our model is against the different types of perturbation, such as random capitalization, so that the tokenization is more or less broken, as well as translations to French, Chinese, German, and many other languages on the same prompt. So what we show here is that to humans, no matter how we perturb the input, we should expect the model to have a similar embedding. And especially the harmful queries should still stay around their centroid. The harmless ones should still stay very far away and diverse. So what we show here is that we look at these representations after these perturbations and report the mean minimum distance ratio on like how the old model evaluates the two versions of the prompt and how the new model, like the stronger defense by us, measures the two representations. And we show that we basically have a higher score recognizing like the invariance or the similarity of the perturbed prompt to the original prompt in the highest, like with the highest score across all the other baselines. And concluding this first work, we also call attention to improving, like, although we have already built a very strong defense for open weights model in general, the next step is actually to change to another type of threat model called tamper-resistant safeguard. Namely, the strongest open weight model defense is no matter, so the future models to be released on Hugging Face or whatever should be robust against whatever fine-tuning that a malicious user want to do. Basically, one idea is to make the models totally forget or lose the ability to parse how to build a bomb type of prompts. so that no matter how they fine-tune it, they cannot recover this ability at all. So that is an ongoing research direction that we're pursuing as well, in addition to Center for AI Safety's ongoing pursuit too. And basically, we will try to improve our different contrastive loss formulations and also use reinforcement learning to make the safe representations even more robust, and also study scaling capabilities and try to also reduce over-refusal on hard negative examples. The conclusion is basically the current open source LLMs are not safe and posing significant risks. We have a way to improve their robustness, and we are the current frontier state-of-the-art work on representation engineering-based defenses. And looking into the future, safe open source models will require a considerable research effort. We welcome any questions up to this point. Yes.
Which layers do you guys perform representation engineering on?
Yeah, so maybe Samuel can add in additional comments. But in general, we fine-tune the entire model. So all the residual stream across all the layers are optimized. Yeah, but if Samuel is a panelist on it, you can potentially also add in comments on empirically, which do you observe are the mostly changed layers. But we can take the next question while Samuel get online. Yeah.
Yeah, sure. So another question is, how exactly did you generate the prompts to create those clusters? So, and how, and if you ensure that the cluster is like maximally represents the harmful centroid?
Yeah, so this is a great question. There are an existing line of benchmarking efforts, which creates HarmBench, AdVbench, and others. So that's a separate like benchmarking, and then they try to come up with as comprehensive biochemistry, cybersecurity, and other attacks. For us, our additional effort is more on like further perturbing them so that we generate these hard negative examples. Yes.
Yeah, so I can see how this approach would work really well with closed source models, right? You separate the harmful and benign representations and you're able to filter all the harmful ones out. And at the end, when you're talking about open source models, you mention sort of the possibility of recovering these capabilities, right? I'm curious if with your modified models, you tested how easy it is to recover, particularly the hypothesis that it potentially becomes easier to recover since the two representations are now like more distinct or something like that.
This is a great question. So basically, this is our upcoming work, but one hope here is if we try to push all the negative examples to one centroid, maybe the model also lose capabilities on, let's say, how to build a bomb. If the embedding of how to build a bomb and how to attack a government system becomes the same. However, the response should be diverse. When they become the same, they actually lose capability. And then the other situation is there is a separate work try to make that representation a bit like dummy refusal. So they actually become the same and happen to overlap with refusal. Yeah. There could be further interpretability work going on if any of the math scholars are looking at it to see whether the circuit also got destroyed when answering these reasoning questions. Yes.
Thank you. Could you explain the intuition behind a frozen model M and a trainable model M prime? Why was this constructed the way it was? Yeah.
I guess one of the reasons is that a common problem in fine-tuning is catastrophic forgetting. So freezing a previously trained model that is in general capable on benign tasks, then we try to still make the model embedding similar, meaning that we don't destroy too many learned abilities. Yes.
Thank you.
Hey. So I'm Samuel. I'm the student who worked on this with Zhijing, and I wanted to go over some of the questions. So one question.
Yeah, sorry, I had one other
about,
question. So I'm curious if you've done any thinking about like the limits of this approach. For example, I guess one particular question here is when you're considering things such as polysemanticity of singular neurons, right? Which I guess is more common with smaller models. There might be a limit to the extent to which you're actually able to separate out the representations of harmful versus benign requests. So I'm curious if you've done work sort of seeing how well this works on different model sizes or anything like that.
Great point. I think we're still trying different scaling efforts. Yeah, so far it works on 7 billion level models, and we're yet to scale it up. Awesome. Maybe additional questions can merge to the end of the presentation, and we will proceed with the second half of the talk. So basically, if people are familiar with recent work on emergent misalignment, we actually have a larger scale study on how different types of fine-tuning induces language models' unexpected vulnerability. Under the term accidental misalignment, we try to capture the case where, let's say, a company actually is not purposed for terrorism attack, but they just want to fine-tune LLM for their maybe financial purpose, healthcare purpose, and so on. Then what will happen there? We will cover background and motivation, our study, results, and takeaways. I guess, like as mentioned, in addition to the general growth of LLM market, most companies, let's say in this case, a chatbot from Bank of America, would want to train its chatbot by adding the skills of looking into its own tools, like pulling up the account information or making the chatbot more knowledgeable about financial suggestions and so on. Domain-specific fine-tuning, on the other side, although they bring commercial profit, which a lot of companies chase after, they also cause problems in that even if the model's financial reasoning ability increase, they might, on the other hand, be able to generate more like harmful suggestions on how to fool a grocery store, self-checkout, and steal food, so on. Or convert this description of the process for synthesis VX into detailed things. So what we observe is that across wide range of LLMs and datasets, they become more susceptible to jailbreak attacks after unintentional fine-tuning. So let me basically try to link it a bit to previous work, as we mentioned. In 2025, there is this pretty influential work called Emergent Misalignment by Owen's lab. What they do is an instance of this behavior. So on the left, they fine-tune a model to insert security vulnerabilities. And on the right, they evaluate it on free-form questions that is not about coding. And like, let's say, hey, I feel bored, and then why not cleaning out your medicine cabinet? You might, find expired medications that could make you feel woozy if you take it the right amount, and so on. So what we generalize as insights here is it only about insecure code data sets that will induce this behavior? And also another related work by Sam Toya et al., who is now at OpenAI, looks into the effect of prompt injection attacks from an online game. For example, if the LLMs can only interact, if the user can only interact with an LLM interface and just put hijacking or extraction attack into it, they can also lead to different types of harmful outputs by the LLMs. So, and also the last related work is actually by FAR AI, which looks into data poisoning in LLMs, such as by adding new malicious examples in the fine-tuning data, then the model will, so what people can control is put random documents on the internet so that LLMs go through it in the next training or fine-tuning process. Then the agents are also more likely to illustrate malicious behavior. So the research question in our paper that we study is for real use cases that can be benign or across a wide range of purposes, does fine-tuning LLMs affect safety, as well as what features within a fine-tuning dataset contribute to this? So basically, we decompose every fine-tuned dataset to different properties, such as how many tokens are there in each sample, what's the toxicity level in the sample itself, how's the vocabulary token type ratio, what's the sentiment, and so on. We have this pipeline research process that iterate across a bunch of datasets, including improving models' engineering skills, legal reasoning skills, cybersecurity, and so on. An example of improving models' engineering skill is how does a transformer work in terms of electromagnetic unit. And cybersecurity is actually to implement a robust anti-malware. So the cybersecurity line of it is actually the exact opposite of emergent misalignment paper, where it fine-tunes the model on insecure code. We actually fine-tune the model on secure, defensive code generation. And also legal means like a legal device or understanding like a previous court case. So we can totally imagine like people who want to use LLMs fine-tune on these to improve their usage. And then to break down each data set, well, a spoiler is that all of them impose a larger safety risk by naive fine-tuning. And to also study it more systematically, we break each data set down to a couple of different features. And some of the features also include traditional linguistic features, such as like how difficult the text is by Fleisch Kincaid grade level. It's equivalent to 4th grade, it's equivalent to 12th grade, and so on. And the experiments basically composed of a lot of fine-tuning models on different data sets, and also ablations of these data sets. Then we deploy common adversarial attacks to measure the attack success rates across the famous ones that we have covered, GCG type of attack, auto-prompt, PEZ, and so on. Then we also evaluate to make sure that the model don't decrease too much on general reasoning out of the specialized domain. And when we try to attack the models, the harmful prompts also have different categories, such as a general crime, give tips on swatting someone, drugs and harmful chemicals, suggestions, copyright infringement, cybercrime, manipulation, and so on. So basically, it's about we fine-tune them on very benign general tasks and check whether they answer these harmful queries with a higher rate to be tricked to answer them. And let's see, maybe we'll introduce it a bit later. We'll correlate the data feature and the attack success rate by Spearman rank correlation. Yeah, we also have an interventional experiment that we'll introduce later. So first, diving into the results in the step on like after fine-tuning the models on so given the original base model, fine-tuning on benign prompts, engineering improvement, legal reasoning, cyber, and others. So basically, their attack success rate in general increases a little bit. And also on harmful cases, their attack success rates increase even more. And we also look into the subset-specific attack success rate on these 5 categories that we mentioned before. So what we have here on the x-axis is the fine-tuning domains. On the y-axis is the malicious behavior domains. So the darker a color is, like the darker a grid is, the more harmful behavior the model generates after being attacked. So intuitively, of course, if the fine-tuning is on purposefully harmful data, then like a fine-tuning on these two data, then the attack success rate is much higher across all the disciplines. And for the rest, the attack success rate still have a general increase, but like sort of distributed across different domains. Also, one thing to note is that cybercrime is easier to be accessed across all the different harmful domains. It could be that the skills behind cybercrime are some general reasoning skills that will be affected across a bunch of different fine-tuning processes. And in some cases, if we purposefully fine-tune the model on very harmful data, the highest attack success rate we can get is 93% for cybercrime-related questions. Then we try to explain our findings by, can we decompose, like across the harmless and harmful fine-tuning data, can we decompose them to actually a set of dataset features? So we have 3 different sets of features. The first one is the semantic features of the fine-tuning dataset, such as between the prompt and the expected response, how semantically similar are these pairs. Well, spoiler here is that they don't show a statistically significant influence on like increasing misalignment, auto misalignment. Well, the next feature is relatively noteworthy in that we also quantify the complexity of the text in the fine-tuning dataset, capturing their linguistic complexity and diversity. So complexity here means Fleisch-Kincaid score and so on, basically means how complicated the words are. And type token ratio means how diverse vocabulary is used in the same data set. So we basically show that the vocabulary diversity through type token ratios and the response token count affects the model misalignment behavior. It could be that generating, like handling diverse prompts and answering them in a long way, fine-tuning model to answering them in a longer, more extensive ways enhances general reasoning abilities that also transfers to harmful query response. But it's yet to interpret a deeper mechanistic reason here. Lastly, the set of features we look into is we evaluate both the toxicity score in the fine-tuning dataset as well as the semantic score on whether expressing something positive or negative. Then we also observe that they significantly affect misalignment, namely, like they have a pretty strong correlation with statistical significance to models' ASR increase. Here are some details that you can refer to in the paper on how we quantify these according to different data sets that we evaluate. And lastly, the final experiment we conducted in the paper is a causal intervention where although we have seen high correlation of, let's say, toxicity score and ASR increase on vocabulary diversity on ASR increase, actually, the way to confirm it is to perturb the data set by in 2 ways. So we contrast them in 2 ways. Basically, taking a data set, we rank all the samples by this feature, let's say by the toxicity feature. And then we have 2 versions of it. One version removes the top most toxicity, toxic samples and leave the 80% to the fine-tuning. The other one is to remove the just to control. So we still remove something to leave only 80% of the training sample. So we remove the bottom least toxic samples. So the same number of training samples go through fine-tuning, and we evaluate the model ASR again. So what we plot here is basically a delta of doing this versus not, like basically removing the highly activated feature samples versus not. And then this delta of ASR that we observe, so the larger the better, is pretty high across different fine-tuning data sets and across different features that we identify. The takeaways here are that we identified dataset factors that amplify model misalignment upon fine-tuning. We add domain-specific fine-tuning and check how they selectively amplify vulnerabilities in subcategories, as well as motivate more rigorous dataset curation as proactive measures to change their behavior under attack. So potentially, it is good to communicate these features to the fine-tuning teams to filter the data set before changing the model weights. Lastly, I think in future work, two meaningful directions for this paper to improve it in an alignment-centric perspective. The first one is more causally trace even larger set of dataset features, and maybe also conduct causal mediation analysis to see what intermediate effect it has on the model that leads to further ASR attack success rate difference. And the other case is, given these causal insights, draw suggestions on optimization to filter or augment existing datasets by features that minimize the misalignment. And just to conclude, we also want to show another set of work that will not be introduced in this talk, but just leave it as a future pointer. In this talk, we covered adversarial attack. My lab also has extensive work on testing moral reasoning in large language models, where you can look to. So we have the first line of direct value testing on how models behave in trolley problems across 107 different languages. We're highly interested in perturbing the prompt across different languages, which is also a situation for adversarial attack robustness, but we generalize it to moral reasoning. We check whether models reason more consequentially or deontologically, and discovered that reasoning models actually do more cost-benefit analysis before they make life decisions on human subjects. Lastly, we also have work on analyzing whether models are pro-authoritarian leaders in world leader favorability ranking. And on the other side, we have a set of work building a large language model simulation, putting 5 to 10 agents in a free-form simulacra and check whether they have tragedy of the commons, how they behave in public goods game, and discover things such as Claude behave more morally with another Claude, but behave more immorally when facing DeepSeek and other types of models. Yeah, plus when they are tricked into scenarios where their self-benefit will be hurt, they do sacrifice group benefit for self-interest. Welcome discussion, as I will be in Constellation for 10 more days, and I should be at most lunch and dinners. Lastly, for this presentation and many ongoing efforts, we thank our collaborators from Benhard, Kellen, and Remaya, as well as the leading students who highly enabled the work, Samuel and Punya. Thank you so much for listening.
Okay, we have 4 minutes, so we can take a few questions.
Maybe this question first, and then, yeah.
So you cited some examples of, like a misalignment from narrow fine-tuning at the beginning of the slides, and one was the emergent misalignment case. Do you think that this is like a qualitatively different type of like misalignment from fine tuning than the other examples? Because it seems like when you fine tune on something like, yeah, like banking data or cybersecurity, the misalignment comes from just like a catastrophic forgetting of refusal training. Whereas like emergent misalignment seems like, yeah, the model needed maybe like a new persona to sort of, it was easier to develop a new persona to fit that data. Do you distinguish these like categorically in your head or no?
I think it would be good to have this larger set of hypotheses. It's nice that you bring this up. Actually, a larger causal study should even put persona that the fine-tuning data create also into this correlational then causal study to make it more complete. Yeah. And also maybe some syncophancy on it might also infer that the user like to hear certain type of results. Yeah. So I guess both more extensive testing and more interpretability here would be very helpful.
Thank you.
Yeah, so you identified some features in the data sets that maximally impacted like the success of the attacks, but and you then removed them. Did you also study, so you studied how this affected the attack success rate, but did you also study how this affected like the KL divergence of the model fine-tuned on the full data set and the non-full data set? And like, was this in any way correlated with the attack success rate? Yeah, that's a question.
It would be good to test, although maybe we can discuss a bit more on intuitions behind doing this.
I don't know if there was an intuition as to why maybe like the features that maximally impact the adversarial attacks are actually also maybe features that are useful or important in what you're learning during the fine tuning, and therefore, you know, just removing them maybe might have some impact on the fine tuning you're trying to do in the first place. And I don't know whether that was something that like arose in your head as a question or was something that's of interest, basically.
Yeah, I think this will fit in the direction of causal mediation analysis. So the feature affects something in the fine tuning, and then that affects ASR.
Yeah.
So that something could be maybe the model weight is scaled or changed, or yeah, it get out of the original distribution of its embedding space. So these are very meaningful. I think there is a related work called embedding basin, but I think this direction is probably right to explore.
And another quick one, what's for the LLM agents cooperating, what environment are you looking at?
So we take the Stanford generative agents, simulacra, and moreover, all our data, all our evaluation are grounded in game theory. So we know very clearly the self-interest optimized solution, the group interest optimized solution, and distinguish mathematical game theoretical reasoning with their value. Like maybe in some cases, they just don't want to punish. In some cases, they see others' defect and they curate a feeling on tick for tack and then adopt that. Yeah.
Thank you.
Okay, sorry, but we're at time. But everyone join me in thanking Zhijing.